Today we're going to bring in a model here, creating this from scratch. We set the unit to millimeter tolerance. We're going to use that. That'll actually ignore anything smaller than that tolerance. And then we set the ambient condition to 85. Now bringing in a step file. This could also be a STL file or an IGES file. We can first bring in the PCB here on top, and we're going to define this as a user-defined material of that will later define an orthotropic, and using the 5%. And so it's going to go through and determine what the smallest size of that object is, and use 5% of that for the tolerance. You could also just specify a length. And then this will go through and defeature any solid as it brings it in. And in this case, these solids are already simple solids, so it doesn't have to do much. So now we bring in the heatsink base, and this we're going to define as a block of aluminum. And later we can go through and define any kind of interface resistance we need, or any kind of contact specifications. So the fan housing will be defined as plastic, and this is going to come in as 4 separate blocks, but the blocks will all make up one solid. Then we take this block here, and we're going to use this to define the fan, and we'll then go put a fan boundary condition on that, which will actually overwrite that object, but it will use that as its location. The only thing left now are the fins, and we're going to select all of these and define them as copper objects. And after bringing these in, they will all be separate objects. We can keep them in one part, then we can look at them quickly and make any kind of modifications we want. If we want to change the thickness to them or move them in some way, change the spacing, anything like that. So here we see the model that's been brought in, and that looks good, so we'll just go ahead and accept this, and we can see no more parts are left, so we hit done and go through. Now if we look closely here, we can see all of the 3D fins, and they are very thin fins, so we're actually just going to go through and select all of these in the model manager and quickly change them to 2D. This will give us the same surface area but take up less elements, and so it'll make our solver run a little bit faster. Now if we were really interested in the pressure drop across the fan, this probably wouldn't be the best thing to do, but for the case of this model, it makes sense. Okay, so next we are setting the heat in the model, so we're going to put some heat into this PCU. So we select the PCU off of the screen. We could also select it in Model Manager if we wanted to, if it was hard to get to, and apply 50 watts to that. Next, we're going to go through and define a solid resistance around that PCU. And solid resistance is a unique feature we have that allows you to put something around it to encapsulate an entire object or an interface between two objects, and it'll find anywhere they're in contact with each other. And it'll put a material that you specify here, plastic, with a thickness of 0.1 millimeters, and determine the resistance between that for both thermal and electrical purposes. Okay, so the next thing to do is actually define that fan. So we come into the fan boundary condition and select that fan object that we're going to use to define it, and input in a fan curve. And fan curves can be found in almost all data sheets for fans. Easy to do, just a difference of the flow rate versus pressure. And here we're just going to do a simple linear curve. And then we're going to define it as a circular fan. So it's not actually, the size of the fan isn't determined by that block. That's really just defining the location. Anywhere where the circular fan isn't, will end up being that material that we defined it as, and we'll give it a little hub diameter here. Here we can see this is in the wrong orientation, so we go back and modify this and change it to the correct orientation. So now the fan is going to be blowing down against the heatsink. Okay, so since we have that done, we can now go and define our materials, our user-defined materials we created. So for PCB, as I mentioned earlier, it's an orthotropic material. So it'll be 18 in laterally, and then through the plane, it's going to be 0.324. And the reason that it's lower through the plane is because you have two thin copper layers Now those layers could be brought in through Gerber instead, but for the purpose of this, we're just kind of doing a simple model to see about how much heat we're going to have. Or sorry, about what kind of maximum temperature we're going to get. Okay, so now we just need to create a mesh, and looking at the default mesh here, it looks pretty good, and we have 60,000 elements, which is a reasonable number for this model, and we're ready to run. And this model will run very quickly. You can see a nice convergence. If you're interested while it's running, there's more information on the back screen, sort of showing what's going on as it goes through. Okay, so that's done, and we read in the results now, and this will automatically give us 2D cut planes on each of the three 2D windows, and then we also have our 3D window showing us the results. So we can go over, look in plane, we can see how the CFD comes in, or the flow comes in, and then quickly diverts and turns. We could also go through and look at the chip itself, and if you see that, it's kind of difficult to see because we have such a big spectrum. So if we go to change to the plane plot, we can, or the plane fringe. Now this fringe is going to update to whatever plane is, so the min and the max of that plane, and that kind of allows us to get a better look, and you can see the hot spot in the middle and how the heat's spreading as it goes out. Okay, so that concludes our demonstration of this simple model. I hope it was